We are going to talk indeterminate forms, about indeterminate forms and L'Hopital's rule here. We have a nice rule which is called L'Hopital's rule. This helps us to find the limits of some ratio of functions when it's difficult to find the limit, right? Actually, we may encounter limits of ratios f over g as x goes to a, and we may end up with expressions like 0 over 0 when we plug in x equal to a. If you have such situations, then L'Hopital's rules say actually you can take the derivatives of the numerator and the denominator separately and take their ratios and take the limit again and look whether you check whether you get a finite value. If you get a finite value, then this is the limit value. Okay, you do this until you get a limit value. Of course, you do this as long as you get 0 over 0. Okay, so let's say we have this expression and we plug in x is equal to a here. We got f of a over g of a, and let's say f of a is 0, g of a is 0, we got 0 over 0. Then we apply L'Hopital's rule. L'Hopital's rule says take the derivative of this and take the derivative of g and take the limit again. And let's say we do this and we put a again, and if we still get 0 over 0, we take one more time derivatives of the numerator and we apply L'Hopital's rule one more time. Okay. You can do as many times as you can, as long as you have 0 over 0 situation. Okay. Of course, we assume here f and g are differentiable, otherwise you cannot take the derivatives of these guys. And we also assume that we stop when g prime is not 0, right? If g prime is 0 and f prime is 0, then you apply it one more time. Okay. Here's how this explains how we use the L'Hopital's rule to find this limit. Okay, continue to differentiate f and g so long as we still get form 0 over 0 at x equal to a. But as soon as one or the other of these derivatives is different from 0 at x equal to a, we stop differentiating. L'Hopital's rule does not apply when either the numerator or denominator has a finite non-zero limit. That's right. That's what I meant actually in the previous part. Let's say limit as x approaches to a, natural log of f of x is equal to L. Let's say assume that. Then what's the limit of the inside function f of x? Limit of the inside function. Limit of the inside function, we use the exponential rules. And we can write ln f of x as actually f of x as e to the ln f of x. We talked about that before. And limit of e to the something is limit of e to the limit of that thing, but e to the limit of ln x f of x is given to be L. So the answer is e to the L. Okay. It says here a may be either finite or infinite. No problem. You can have both. Okay, actually this graph helps you to understand the L'Hopital's rule better. I'm gonna just what it's saying is this makes good sense of the L'Hopital's rule. Why are we doing this L'Hopital's rule? Limit of as x approaches to f of x over g of x is equal to limit x goes to a f prime over g prime. It makes sense because look at the L'Hopital's, look at the slopes or the tangents at a. Look, the limit of the ratios. So you can consider. Okay, we have f. I'm sorry, just a sec. We have f, and we have the this y is a linear approximation at x is equal to a of f, and this tangent line at a for g, which is g prime a x minus a, is a linear approximation at x is equal to a for g. Okay, because g of a is 0, right? F of a is 0. You remember the linear approximations. So actually, since they are linear approximations, and since we are taking the limit, a limit as x approaches say f of x, g of x is going to behave as their ratio of their linear approximations. That's why we take the ratio of the two, and x minus a's are going to disappear. So we have f prime x over g prime x as limit x as x goes to a. So this graph makes good sense of why we have the L'Hopital's rule. Okay, I'm gonna, I think, skip Cauchy's mean value theorem. Let's see. One can understand it. Maybe you may need it, so let me explain it to you. So let's say we have two functions f and g that are continuous on the closed and bounded interval, and let's say they are differentiable in the open interval, and assume that g prime is not 0 in the open interval, and it says you can find c in AB such that the derivative at c over the derivative at g is going to be equal to f of b minus f of a over g of b minus g of a. Actually, this comes from the fact that you apply mean value theorem to f and g separately, and we have b minus a coming in the denominator there. Just equating the b minus a's, you get such an expression. So this could be useful sometimes, Cauchy's mean value theorem. Okay, I'm gonna skip that.